Good afternoon, everyone. I hope you're having a great virtual VMSG. Today, I'm presenting results from fieldwork that colleagues and I conducted in January 2018, back when such things were still possible. I'd like to quickly put a big thank you out to INITA, the Nicaraguan monitoring organization that made the work possible, especially Martha. Her knowledge and expertise were invaluable for this work. Masaya is a very interesting basaltic volcano located on the Central American volcanic arc. Its Santiago crater hosts one of the few active lava lakes in the world, and lava lakes are currently a hot topic with the appearance of a new lava lake at Kilauea. Masaya also has a really interesting eruptive history, being one of the few known sites of basaltic Plinian eruptions, the others being Etna and Tarawera. Degassing changes provide clues as to magma ascent dynamics occurring in the volcano, which might provide warning for future eruptions. This makes gas emissions a common monitoring target. SO2 is the most readily measured volcanic gas due to its high plume concentration, low atmospheric abundance, and strong UV and IR absorptions. We wanted to quantify SO2 emissions using an SO2 camera, then verify the camera measurements using the more established traverse methodology. We set up our camera, the red star in the diagram, around 5 kilometers away from the vent, the red triangle. Masaya is a great choice for these measurements, as it has an easily accessible road to the west of the volcano for traverses and has a large gas flux. It ranked 18th for SO2 emissions between 2005 and 2015, averaging 867 tonnes per day, or roughly 10 kilograms per second, according to Khan and others in 2017, using the satellite only. The SO2 camera is a great tool for obtaining frequent measurements of SO2 emission rate from the volcano, making it able to capture rapid changes in degassing. There are 2 individual cameras in a single SO2 camera, as pictured on the left here, one to see the SO2 and the other to remove the effects of aerosol. However, the camera can only measure the optical depth of gas present, shown on the right. Optical depth is proportional to SO2 column density, but this constant of proportionality changes depending on the lighting conditions, so it must be calibrated using a spectrometer pointing into the camera field of view, or gas cells of a known concentration. Unfortunately, when we applied the 2 different calibration methods to our optical depth measurements, they didn't agree, as can be seen in the graph on the left, with orange for the cell calibration and purple for the spectrometer calibration. Even worse, neither agreed with the 4 simultaneous traverses we did on the same day, shown as the scatter points. A clue lay in our spectrometer measurements, which showed that the spectrometer did not even agree with itself when using different analysis wavelength ranges. Here, 306 to 316 nanometers, and 312 to 322 nanometers. The key problem is that at this point we hadn't corrected for light dilution. Light dilution is a known issue caused by photons that have travelled through the plume scattering out of the field of view of the camera, which are then replaced by photons that have not travelled through the plume. It appears in visual imagery, as can be seen in this lovely photo from my mapping project in Spain, although the effect is less powerful in visible light, especially in redder colours. You can see that the signal of the hillside gradually reducing with distance, making the furthest hills more sky-coloured. Artists use this trick to convey depth, and this unfinished Da Vinci painting, Virgin and Child with St. Anne, is a particularly fine example, demonstrating a washed-out background. The main issue with dilution is that optical depth, and hence SO2 column density, follows the natural logarithm of transmission, rather than being linear. This means that if we average a 1000 ppm spectrum, here shown in blue as the lowest transmission, with a 0 ppm spectrum, which would be a line across at 1, we get the green line, which has a significantly higher transmission than the orange, real 500 ppm spectrum. Critically, this means that the 50% dilution we expect at 5 kilometers from theoretical calculations of dilution actually causes a greater than 50% drop in measured SO2 slant column density. You can see that SO2 transmission is higher in 312 to 322, so the effect of the logarithm is less, resulting in higher column densities compared to 306 to 316 nanometers, as seen on the right. The difference between the column densities retrieved at different wavelength bands has previously been noted by Mori and others in 2006, but we thought it might even be possible to correct dilution using this difference. Our method simulates light dilution using the forward model present in IFIT, which Ben Essie briefly touched on earlier. First, we do a standard fit to get the parameters of the spectrometer and lighting conditions. We then create spectra with a range of different SO2 concentrations and light dilution factors, which can be thought of as the fraction of light arriving at the camera that has not come from the plume. These spectra are then reanalyzed using two different wavelength ranges mentioned before, creating a lookup table of SO2 column densities that can be then applied to real spectra. The graph on the right is an example of a very sparse lookup table with model SO2 column densities in 250 ppm steps from 0 to 5000 ppm and dilution fraction in 0.2 steps between 0 and 0.8. Notice how even at a dilution fraction of 0.2, the column densities retrieved can be far lower than the value put in. Let me stress that the last point on each curve has a model input of 5000 ppm, so at high column densities, increasing the SO2 present in the model reduces the retrieved column density using standard analysis, which is shown by the backward curve. We created a lookup table specific for our spectra from Masaya, then applied it to correct the readings. The uncorrected measurements are in orange on the left, while the corrected show an almost 5 times increase in the blue. The lookup table has also corrected the systematic curve away from 1-to-1 that we saw in uncorrected measurements, so the two wavelength windows now agree on the SO2 column density. If you cast your eyes to the right, you can see the time series of the measurements of 306 to 316 nanometers, showing the corrected measurements again with much larger SO2 column densities. Also visible is the removal of the sort of cap present in the uncorrected SO2 in orange, leading to a more dynamically varying result. However, the lookup table seems to perform poorly on low column densities, where it's not well constrained. The light dilution is roughly 50%, which is in line with our theory. Perhaps the best way to emphasize the difference between the uncorrected and corrected measurements is with the camera imagery calibrated with the spectrometer being uncorrected on the left and corrected on the right. I'll let this run for a bit, but we can anticipate that the large difference in column density will cause a correspondingly large change in measured emission rate. And indeed, this is exactly what we see. Note that we have applied a different correction method that comes from Campion and others for the cell calibration that unfortunately I don't have time to go into here. But notice the good agreement between traverses and emission rate from the camera using both calibrations, with the averages all around 1,800 tons per day. This is a large step up from the uncorrected calibration methods, and a paper showing this work is currently under review. And if that's not enough to convince you, then here is a further measurement day where unfortunately we had no spectrometer running. However, you can clearly see the great agreement between the other camera calibrated emission rate and traverses, this time averaging a lower 1,200 tons per day. I'd really like to get into the timescale of the change in emissions between the 2 days, but we'd need further campaign measurements. So our measurements are consistent with previously reported DOAS traverses at the volcano, well within the 1,000 to 200 tons per day to 2,000 tons per day bracket since 2017. This is a little higher than satellite measurements I mentioned earlier, shown as the white bars, though this may be due to increased activity since the formation of a subaerial lava lake in December 2015. Interestingly, SO2 traverse measurements spiked some 6 months after the lava lake formed, then returned to a slightly higher value than before the lava lake formed. Though this is not seen in readings from the NOVAC scanning network. I just wish Khan had published another year of satellite readings to settle the issue. So, to sum up, we have created a new model for correcting light dilution in UV spectra. The model highlights the importance of these corrections, as without them there is a large underestimate in the readings, as well as a worrying maximum SO2 column amount that it is possible to measure at that wavelength. The method uses the discrepancy between the two different wavebands to quantify and correct SO2 column densities. These corrected column amounts can then be used to accurately calibrate an SO2 camera, giving what we think are accurate emission rates. Thank you for listening.